Vanakkam. Welcome to this course on biomedical instrumentation. We started looking at EEG. We looked at the introduction to EEG. Remember what it is that you are trying to measure. Millions of neurons are active at different levels. They are not simultaneously active at the same level. If that happens, that is a different disease. Millions of neurons are active at different levels at a given point in time. You are trying to record from outside the scalp. Now, this situation can be compared to, let us say, the situation outside a cricket stadium. Let us say you are standing outside a cricket stadium and all you are hearing is some noise. Oh, some noise. Yet, when a large group of people decide to chant together, for example, when I used to watch cricket, nowadays I do not watch cricket. When I used to watch cricket, this was a famous chant, Sachin, Sachin. That when thousands of people together chant, you can hear that from outside. Or they will say, India, India, like that. You can hear that from outside because thousands of people are shouting the same slogan at around the same time. You cannot hear individual person's voice. You do not know what individual neuron is doing, but you know the net output, the ensemble output of a large number of people. Note that there must be time synchronization that must happen between these people for them to chant. Let us say one person is saying Ind, in India, India, one person is saying Ind, the other person is saying Ya. You will not be able to, at a given point in time, when one is saying In, the other is saying Dia, then you can't really hear that. There must be time and phase synchronization that must happen, and that somehow happens in these crowds, and that is what you are hearing. From outside the stadium, not from inside the stadium. From outside the stadium, you are just standing out, just outside the stadium, you are hearing Sachin, Sachin, and applause. Now, what you are trying to make out is from which region in the cricket stadium this noise is coming, this chanting is coming. Which person or which area, if not you cannot identify a person. Some cricket stadiums have capacity above 100,000, 1 lakh people are there. Which person shouted Sachin at which point in time? Very difficult for you to find out. If you cannot identify that, at least which rough region shouted what at a given point in time is something that you are interested in. This is only an example for parallelism, so you can understand. How is it relevant to EEG? In EEG, this is similar, perhaps even more amplified. The situation is even more amplified because you are having millions of neurons that are active at different levels, and I am measuring from outside, and I am trying to see what is happening in a given region of the brain. I already mentioned that is the volume conductor problem. I need to know, in a previous video during electrodes we discussed, I need to know forward model of conduction in a given set of tissues, conduction in excitable tissues or excitable cells, and inverse model that predicts what is happening at a given point in time when something is happening, or rather what is happening from the measurement, what you are having from measurement to activity. This is what I am measuring. Given that this is the activation level that must be there to measure so much activation, perhaps so much must be the activation in a given region. That is a problem. The problem is, it turns out that multiple combinations of activation levels in the neurons may give rise to a given output. So, plenty of obfuscation, plenty of doubts, noise, everything is there in EEG. This is something that I wanted to discuss in the previous video. Now, we will get to this business. So, in this class, we will look at the block diagram of EEG, and montage systems in EEG are measurement schemas in EEG. Now, how do you measure? Mostly when you say EEG, you are referring to scalp electrodes. Electrodes are placed on the scalp, They detect the brain's electrical signals. Electrical signals means essentially not individual neurons, but rather field potentials of a group of neurons. I already mentioned, for you to measure something at the scalp, you need to have 4 to 6 centimeter squared area of neurons activity. That represents approximately anywhere between 10 to 100 million neurons. That is what. So, you are at least looking at a million neurons. Of course, I could in the present day there are 256 and 512 channel EEG, but that does not really remove, it improves spatial resolution by a little bit, but it does not remove the volume conductor problem. If anything, I have more data that I do not understand what it is. So, more data does not always mean that it is better. So, you need to be cautious. When it comes to spatial resolution, you still need to be cautious. Okay. Electrodes are placed on the scalp according to a scheme. There are some standard schemes we will look at. There are this standard 10-20 electrode system. We will look at that in one of the future classes. And then there is a electrode interface board. So, these electrodes are connected to this board, and then from this board there is a single cable that goes to the electrode and montage selector. This essentially is used to ensure that the configuration that you are choosing to measure from is the configuration that you have given. So, it ensures proper electrode configuration so that appropriate signal accuracy is seen. And then amplifiers essentially boost weak signals. That is the idea. Amplifiers essentially amplify, they boost weak signals and apply the appropriate filters. First is high pass filter. What is the frequency range? Note that EEG will have significant signal power, critical signal power even at frequencies as low as 0.1 hertz. So, high pass filter above 0.1 hertz. Okay. Low pass filter perhaps below 50-60 hertz, 40 hertz. Most of the activity until in the last class we saw beta, alpha, delta and theta and gamma. Gamma has activity above 30 hertz, but most of the activity is below 45-50 hertz. So, that low pass filter you may have below 40 hertz for example. The details we will see in future. And a notch filter at 50 hertz, in India 60 hertz in the United States to remove the common mode noise, that is the power line interference. So, essentially to remove noise, and then analog to digital converters, so that I could store this in a computer and then post process this analog to digital converter, minimum you need 16-bit, preferably nowadays 24-bit accuracy, 24-bit resolution, not accuracy, 24-bit resolution ADC is now available. This essentially digitizes the signal so that it can be post processed in a computer. Meanwhile, you can also view the output on an oscilloscope, and you could also have it printed so that you could take it with you to the clinician. So, there is a chart driver and there is a motor, like in ECG there is a motor, there is a pen driver, there is a pen motor and there is a chart motor that essentially drives the chart and the ink, and then you have this ECG that looks almost like noise. This is what you have. Meanwhile, you have a system to test and calibrate the electrodes. Nowadays, you also have a system that electrode testing system will also have facility to measure impedance. Preferably, impedance must be high quality EEG, impedance must be below 5 kilo ohms. This is the preferred value. And you choose a montage. What is a montage? A montage is a systematic method to measure and display EEG signals, or a structured way to display and measure EEG signals by arranging electrode pairs for appropriate activity interpretation. Essentially visualizes patterns and abnormalities. Depending on the application, you can choose whether you want to have bipolar montage or referential montage. In bipolar montage, you compare activity of one electrode with the activity of the neighboring electrode, with the nearby electrode. This essentially highlights spatial phase reversals that happen within a relatively small zone of interest. Note that even if these are neighboring electrodes, you are still talking about a few centimeters apart, again millions of neurons apart. So, it is not that high resolution when it comes to spatial resolution, remember that. But still you may be able to get some local changes. Local means local within that space. Some examples are changes that happen, from the front to the back, because frontal lobe is responsible for executive decision making and prefrontal lobe is responsible for this executive decision making, other such things, and then transverse lobe is responsible, different regions, then side to side activation, different regions in the, when you go from front to the back, are responsible for different activations. So, you may be able to detect local effects or phase reversals in the local changes. And the other method used to compare activation of a given electrode, for example, this FP1 with a distant referent electrode. For example, with reference to a mastoid or with reference to vertex. This is useful to compare amplitude changes of a given electrode and locating the activity of that electrode with reference to some common reference. We have seen this previously. In the ECG, we saw bipolar leads and unipolar leads, those that have a common leads. What are the unipolar leads in ECG? The augmented limb leads, we saw that. Of course, the precordial leads are there, but I am talking about unipolar augmented limb leads that have a common reference. Likewise, you have a common reference in this. Why do montages matter? Because it helps to localize and pinpoint and specify brain activity. I mean, localize means what? In a rough area. In a rough area, it helps us, at least it helps us to localize which hemisphere it is in, which lobe it is in, that level localization. So, really when I say localization, don't take it to heart that I am going to get which neuron is active, which region of the hippocampus is active for this function. I mean, that is like going a little too much, right. So, you are going to have relatively compromised spatial resolution. That's going to be a challenge throughout, right. It is going to help pinpoint brain activity, but it is quite useful in detecting and diagnosing epilepsy and seizure disorders, and in detecting sleep stages of sleep stage. In those things it is quite accurate and quite helpful. In particular, it has an extraordinarily good temporal resolution. Now, that is something that is unmatched when it comes in EEG. So, that is one. The other is lateralization. I already mentioned this. Let us say I am interested in comparing activity across both brain hemispheres to detect asymmetries. I mean, this is something that we have worked on, and recently also published. One of our papers on this is still under review in scientific reports, where we have compared the asymmetry index between healthy young and healthy elderly when the person is performing a task with the right and the left hand using EEG and also using fingertip forces. This is a paper by one of my former PhD scholars. She graduated already, her work. It also provides a structured way to interpret EEG patterns and essentially abnormalities, and it is purpose specific. Depending on which situation and which application, I can use different montages. So, it essentially serves different clinical and research needs. What are the common montage types? Longitudinal bipolar type, electrodes placed front to back or side to side to view activity along the anterior posterior axis, or transverse bipolar, side to side to view left and right brain activity. Now, with this we come to the end of the EEG discussion. Some more things to remember. What are some of the characteristics expected from the EEG system? Input impedance must be greater than 100 mega ohms. I mean, nowadays it is definitely more than 10 giga ohms minimum. Current commercials ones have greater than 10 giga ohms. Okay. Then ADC resolution minimum 16 bit, nowadays 24 bit is available. Then frequency response (0.12) say 45 or 50 hertz, 0.1 to 100 hertz is available. Then noise characteristics, noise must be 1 microvolt, change per 1 microvolt must be less than 1 microvolt RMS. This is available. Less than 0.1 microvolt is also available. CMRR minimum recommended is 100 dB, 110 to 120 dB CMRR is now available. With this we come to the end of this video. In this video we looked at the block diagram of EEG and the montage system in EEG. Oh, one more thing, what do these montage systems actually represent? We just discussed the case of the stadium and the sound. Now, what do the montages compare? Now, that is like attempting to measure earthquake using seismographs. Which montage you choose depends on which location of the seismograph earthquake measurement system, from which location you are trying to measure, essentially can be compared to the montage that you are choosing. Something to think about or compare. Of course, examples are only examples, but the content really matters. Okay. So, with this we come to the end of this video. Thank you very much for your attention.